Good day, grade 12 learners. Welcome to today's technical science lesson. My name is Musa Zulu. This lesson is brought to you by the Gauteng Department of Education in collaboration with Cybono Discovery Center. Okay, grade 12. Today again, we are still on paper 2, still doing paper 2. And we are still doing the knowledge area, matter and material. Again, our topic is still also on organic chemistry. Organic chemistry, remember that we did say is a very, very broad topic. So we're still doing organic chemistry. We started with organic chemistry and we looked at a lot of things in organic chemistry, your homologous series, your functional groups. We also looked at naming in organic chemistry and all of those things. Today, we are going to be looking at physical properties, the physical properties in organic chemistry. So we're going to be looking at those physical properties for today. This is part of paper 2. And usually in your question paper 2, you'll find this as being question 3. So this is around there. It is usually question 3. A very, very challenging question to most learners. However, we'll try and break it down today and try to make things easy and more understandable when it comes to this question. It shouldn't be a difficult question because when you break it down, you would find that it becomes very, very simple. So bear with me, go with me throughout this lesson as I try to unpack it for you. All right. So lesson objectives, what we expect that you must be able to know after this lesson is the fact that we must be able to differentiate, let us be able to differentiate between intermolecular forces and interatomic forces. So there are two forces that we want to be able to differentiate between grade 12. Let's be able to differentiate between intermolecular forces and interatomic forces. And I will be emphasizing on these ones, the intermolecular forces, because these are the ones that we are going to be dealing with the most when it comes to that question 3 of paper 2. Very important question that I want learners to get, and I don't want this to become a problem every time, that question 3. Let this question 3 become very, very simple for us. Number 2, we must be able to know and define all physical properties. So we look at the physical properties. We must know all physical properties that we are going to look at. I will show you how you can just simply abbreviate them so that you can simply remember all of them. And then you must be able to define all of them as well. Okay? You must be able to know the different intermolecular forces according to their strength. So by the end of the lesson, I expect that we'll know the different intermolecular forces within organic chemistry, of course, and within our scope at our level at grade 12. So we'll know these organic or intermolecular forces, and you must know them according to their strength, meaning you know this one is weak, this one is stronger, this one is the strongest. Okay? Right. You must also know the factors determining the intermolecular forces of the compound. So there are these factors that will determine what intermolecular forces are we going to find in this certain compound. So we must know these factors that will be determining these intermolecular forces, and they are going to help us. Okay, and then you must be able to use these vectors to answer questions based on physical properties. So the factors that we said we need to know are very, very important. So once you know them, it will make it easier for you to be able to answer all the questions that are based on physical properties. So those would be our lesson objectives for the day. That's what we would expect that people are able to do after the lesson. Okay, so what is it that you must come here knowing? What is your pre-knowledge, the pre-knowledge that is expected of you for you to be able to understand this lesson easier? Well, we expect that you are able to at least define a homologous series. Okay, you must be able to define a homologous series. We've done this since the beginning of our organic chemistry sessions. We have defined a homologous series. I hope it shows the importance of this definition. This definition is very, very important, grade 12. Each and every one of us must be able to define a homologous series and also define a functional group. These two are perhaps the most important things. If you are able, you know your homologous series and you know your functional groups, this will make life easier when dealing with organic chemistry in grade 12 technical sciences. So you must be able to define a functional group. And you must be able to identify a homologous series of a compound from what? From just looking at the structure of the functional group. So by looking at the structure of a functional group, say here is a compound here. You have a compound and this compound looks like this. So by looking at the structure of the functional group, what's the structure of the functional group? In this case, it will be this guy here. This guy here will be the structure of the functional group. So by looking at the structure of the functional group, I can say that the homologous series here is a what? Is an alcohol. So by looking at the structure of the functional group, you must be able to identify that this compound belongs to alcohols. So you're identifying a homologous series there. But you must also be able to identify the homologous series from the name of the compound. So that means by looking at the name of the compound. For example, if we were to name this compound, since it has 2 carbons, we would say it is eth carbons, it is eth an dash 1 dash all, because you have the OH there on carbon number 1. So it becomes eth an dash 1 dash all. So by looking at the name, can you identify from which homologous series does this compound belong? I look at the name ending of the compound. It ends with all, and homologous series that end with all are the alcohols. So alcohol will be the homologous series there. So how am I identifying these homologous series? By looking at the structure of the functional group, or by looking at the name, specifically the name ending. The name ending will be the one that always tells you to which homologous series does a certain compound belong. So these are the things that you must be able to do as we embark on this lesson for today. Okay, so let's give you some questions that maybe you can simply answer quickly as we go along to try and see if you are able to do that. First question would be, can you define a homologous series? The next one, define a functional group. And the next one, consider the following table and identify the homologous series of each of the compounds. So you look at the table, you say, what will be the homologous series of each of these compounds? To what homologous series does compound A belong? To what homologous series does compound B belong? To what homologous series compound C, D, E, and F? So how do you identify? By looking at the structure. If you see the structure here, here's the structure of the functional group. This part here will tell you to what homologous series does this compound belong. When you come to this one, you have a name. You must be able to what? To identify the homologous series by looking at the name, looking at the name ending. This name ending will tell me the homologous series of this one. If you remember last week, we did that R5 catch table. If you have your R5 catch table, it will be coming in handy right now, because your R5 catch table has the structure of the functional groups. Your R5 catch table has the name endings. So by looking at the name ending, you can now just match it to the homologous series to which it belongs. By looking at the structure of the functional group, you can match the compound to the homologous series to which it belongs. Okay, I look at C here. Here's the structure of the functional group. By looking at that, I should be able to identify the homologous series. I look at D, the name ending in there or ane, I should be able to identify to which homologous series does this compound belong. I go to E again, it's a name. That means I go to the name ending. Here's the name ending al. The name ending al tells me that this belongs to a certain homologous series. Again, I go to F. I look at the structure. What is it that tells me that this belongs to a certain homologous series? It will be this right here. This will be the structure of the functional group. So by looking at this, I should be able to identify the homologous series by either looking at the structure and also by either looking at the what? At the name. So I hope people have really went through and answered this question quickly as I was going through, or in your head as you are looking at it, you're like, oh, I see that structure, must be a ketone. Oh, I see that that name ending, it must be an alkyne. Oh, I see that structure, it must be an alcohol. Oh, I see the structure, it must be an alkane. Just by simply looking and just by knowing that R5 cache table that we spoke of in the previous week. Okay, so let's see how you will be expected to answer the questions. The question of define a homologous series as we have defined it before, it is a series of organic compounds that can be described by the same general formula and where each member differs from the next by a CH2 group. That will be a definition. It's a definition that we must know, a definition that will be given a 2 marks or nothing in the exam. So it is important that we know this definition and we can define it exactly according to the examination guideline. I will always stress that we define according to the examination guideline and nothing else. Define a functional group. Functional group is defined as an atom or a group of atoms that determines the chemistry of a molecule. An atom or a group of atoms that determine the chemistry of a molecule. Again, under the 2 marks or nothing there. Either you get the 2 marks for the definition or you get 0. There is no reason for any of us to get a 0. Because you can't be at a stage where you are at a grade 12 level and you are unable to just read and memorize few words. It is impossible. The fact that you are in this class means that you are able to read, you are able to write. So then you should be able to at least memorize definitions. Okay, all right. So the first compound there, if you look at the structure there, if you go back there, this structure, we have a C double bond OO and it is surrounded by 2 other carbons. So we should say this is a what? Is a ketone. Okay, and if you look at B here, if we're going quickly, we have ine as the name ending. That tells us that we are dealing with an alkyne. You look at this one, you have OH there, bonded to a carbon there. This should tell us we are dealing with an alcohol. Here you have ane or ane as the name ending there. That tells us you are dealing with an alkane. And then here E, you have al as the name ending. Al tells us we are dealing with an aldehyde. And then lastly, F, you have the triple bond there between the carbon atoms. Triple bond tells us we are dealing with an alkyne again. You are dealing with an alkyne again. So those are the compounds. We have been able to identify these. Those are the homologous series. We have been able to identify the homologous series by looking at the structure of the functional group, by also looking at the name ending. These are things that we did in previous week, and you must be able to do these things by now. That's going to help you a lot as we embark on this lesson. So here's the answers that we've looked at here: the ketone, the alkyne, the alcohol, alkane, aldehyde, and again the alkyne. Those are the ones that we're expected to get. Again, I will emphasize the use of those tables. Might be the R5 cache that I showed you the previous week, or any other table or any other method you use with your teacher in class to remember all the R5 homologous series with their structure of the functional group, with their name endings. Have a set of something that you are using to remember these things, because they become very, very important. That basic knowledge that we're dealing with in the previous 2 weeks becomes very, very important in understanding organic chemistry moving on. It becomes the basis. It makes even this question that we are saying is usually a tricky question to become easy, because there is really no reason. You will see as we go into it deeper today that you shouldn't be saying this question is difficult. In fact, we should be making it one of the easiest questions to answer in paper 2. Okay, so the terminology that we are going to be looking at for today is that we are going to be taking types of intermolecular forces. So those are the new words that we are going to be encountering. We're going to be encountering words like London forces or dispersion forces. Okay, what are London forces? These are forces that are between non-molar molecules. Okay, you understand nothing of this for now, and it's okay. Okay, we'll take it step by step. And then number 2, dipole forces. What are dipole forces? Forces that exist between 2 polar molecules. Okay, and the third one that is should be new to us is hydrogen bonding. What is hydrogen bonding? Hydrogen bonding speaks to forces again. These are forces that you find between or forces between molecules in which a hydrogen there is covalently bonded to either an oxygen, a nitrogen, or a fluorine. For us, it will be bonded to an oxygen. We will not be looking at ones that are bonded to nitrogen and fluorine. So again, our scope goes down there a little bit. No need for us to stress ourselves about nitrogen and fluorine. We'll only look at this. And I'll also make it easy because I'll just identify for you which ones are going to have hydrogen bonding. Okay, so hydrogen bonding is a type of intermolecular forces. However, it is important that we know that hydrogen bond is just a special type of what? Dipole-dipole forces. So it should be falling under dipole-dipole forces, but it has some specifics, things that make it special. So those things, they make it to seem like a different type of intermolecular forces. However, it is a dipole-dipole, but a special type of a dipole-dipole. It was given a name, hydrogen bonding. Okay, so that's the terminology. Okay, what other terminology that we should be familiar with for today's lesson? We should be able to define the following terms. These are the physical properties that now I was talking about. Okay, we should be able to define boiling point. I abbreviated BP. Okay, it makes it easy. I will show you as we continue with the lesson. I abbreviate boiling point, BP. So I have BP, boiling point, the temperature at which the vapor pressure equals the atmospheric pressure. Here's what I would ask you to do, grade 12. I would ask you to simply memorize this definition for boiling point, especially all the definition of these physical properties. Memorize them, but think of them in terms of your general knowledge. What are we saying when we're saying something is boiling? This is a state where something turns from a liquid to a gas. So when you are thinking of them and you are trying to reason, trying to answer a question, think of it in terms of general knowledge. Yes, there's a definition here. I want you to memorize the definition and write it according to the examination guideline. However, I want you to think of them generally, to say, here we are having a liquid that is turning to a gas. This is what we mean when we say something is boiling, so that it will give you some sense, and then you'll be able to then come up with answers to certain things. Melting point is the temperature at which the solid and liquid phases of a substance are at equilibrium. Temperature at which the solid and liquid phases of a substance are at equilibrium. Again, think of something melting. What's happening when something is melting? That's when something changes from solid to liquid. Okay, just think of them as the general, or in general. What is happening when something is melting? You have ice, it was solid, and it is turning into what? Water, which is what now liquid. So just think of them like that. So how do I abbreviate melting point? I say MP. Okay, BP for boiling point, MP for melting point. Okay, I keep the abbreviations in my head, by the way, they help me. Okay, then I have viscosity. Okay, what is viscosity? This is the property of a fluid to oppose relative motion between the two adjacent layers. When you have two adjacent layers, there is going to be that opposition that occurs there. But how can we think about it in general? When you take viscosity, grade 12, you are just simply talking the resistance of a fluid to flow, just in general. This is in general. This is not the formal definition, by the way. So I've given you the formal definition. Now in brackets, I'm giving you the general way of thinking about it, so that you'll be able to come up with answers. So when you think of viscosity, just think of the resistance of a fluid to flow. What do I mean, resistance of a fluid to flow? You have to think about it. If you think about cooking oil versus water, these two fluids, both of them are fluids, okay? If you pour them down, they are not going to flow at the same rate. You'll find that water runs faster, right? Wherever you're pouring them, say you are pouring them, water is going to run faster compared to the cooking oil. That tells you that cooking oil is going to resist more to flow compared to water. So what do you say about those two? They have different viscosities. That's what we mean when we're talking viscosity. So they have different viscosity. The cooking oil is going to be what? More viscous. That's what we say. We say it is more viscous because it has a higher viscosity than what? Than the water. That's why you see the water not resisting. Its resistance is extremely less as compared to the cooking oil. Take the cooking oil, compare it to honey, for example. You would find that cooking oil will have a lesser viscosity compared to what? Honey, because honey will flow even less. Take that honey, compare it to syrup. Again, you will see the trend there of having more resistance to flow. The more the resistance to flow, that means the higher the viscosity. That's what is viscosity. So I want you to know the definitions formally, but I want you to think them in terms of general, because the issue is going to be reasoning based on these things. So that's going to become very, very important. Grade 12. And then how do we abbreviate this one? I just usually say viscous. Okay, viscous. That's the abbreviation there. Okay, then vapor pressure. What are we talking about? This is the pressure exerted by a vapor at equilibrium with liquid, with its liquid in a closed system. The vapor, okay, or the pressure exerted by the vapor. Now, vapor pressure might be new to you, grade 12. So this might be maybe a little bit difficult for you to then imagine and generalize. So let me make it easy for you. Vapor pressure is new to you, but the word pressure is not new to you. The word vapor is not new to you. You must be having some understanding of these two, okay? Usually we say for us to have vapor, something must boil, turn from liquid to gas, okay? Once something has turned to gas, we say it's vapor. Water vapor, we'll remember from the lower grades, okay? Okay, then when we think of pressure, it is some force that is exerted over a certain area. That's pressure, okay? So what do we mean when we say vapor pressure? We are talking about the pressure that is exerted by a vapor, okay? So when are we going to have this vapor pressure? Once something has turned from being liquid to a gas, okay? Once something has turned from being liquid to a gas, it will then exert this force. So think of a container. Take the metal container, put water in it, and close it, and then put it in water. What's going to happen? The water will start boiling. After the water boils, it reaches its boiling point. It changes from being liquid into being gas. So what's going to happen? All of the water changes. It's no longer liquid. It becomes gas. So what's going to happen? Usually you find that this container does what? Start to expand. Think of it. The container will start to expand. Maybe you can even think of a plastic bottle. Usually you find it, if it's closed, it is now expanding. Why is it expanding? There is vapor pressure there. The vapor that is inside the bottle is exerting pressure on the what? On the container that is closed, okay? So, for me to have vapor pressure, or for me to have high vapor pressure, it means something must boil easily, okay? For me to have high vapor pressure, it means something must boil easily. So it must boil, it must turn into gas easily. Then I will have more vapor pressure. So for things that take time to turn into gas, those things are going to have less vapor pressure. Okay? I hope you get me there, grade 12. For things that take time to boil, things that will take time to turn into gas, they are not going to have high vapor pressure because they don't have a lot of vapor in them. Okay? For things that, let's say you have water here, okay, let's say it's a closed system. Let's close the system. And then we have honey here. Which one is going to have a higher vapor pressure here? If you both expose them under the same heat, you would find that this one will take time to turn into vapor. It will take time to turn into vapor, right? Let's write more time. This one will take less time. So the one that is going to take less time will have more vapor in it. Therefore, we are going to say it has higher vapor pressure. We are going to say it has higher vapor pressure. The things or the substances that are going to turn into gas quicker, they are going to have higher vapor pressure. But the substances that are going to take time to turn into gas or into vapor, these ones are going to have low vapor pressure. I hope the issue of vapor pressure is now making sense to you, to say, what do you mean by vapor? Something must turn into vapor, then it will exert that pressure. Okay, now that is your vapor pressure. So for me to have more vapor pressure, something must then boil. It must turn into what? It must turn into a gas. I hope the vapor pressure thing is making sense. How do we abbreviate vapor pressure? We say VP. So what is our physical properties? Our physical properties goes as follow: BP, MP, Visco, and VP. BP, MP, Visco, and VP. Okay, BP, boiling point, melting point, viscosity, and vapor pressure. Okay, right. That will be our terminology. So let's dive right into it to make sure that we cover everything in time. Great talk. So what are we looking at? We are looking at the intermolecular forces, and we also want to look at the interatomic forces and try to just differentiate between before we can dive into the intermolecular forces and do a deep dive there. Let's have a difference between intermolecular forces and interatomic forces. What are these things? Well, we'll start with interatomic forces. Interatomic forces, these are forces or bonds between the atoms within a molecule. Now, this is not a definition that you're going to be asked because you do not find it in the examination guideline. I'm just trying to give you this understanding of interatomic forces. Interatomic. So these are forces that you are going to find in one molecule. For example, a molecule like this one. Okay, these are forces that exist between one atom and another atom. The forces that exist there are called interatomic forces. They are called interatomic forces because they are within the molecule itself. One molecule has these forces. These forces are holding the oxygen and the hydrogen together. Okay, these forces are holding the oxygen and the hydrogen together. So there will be that a force here, there will also be that force. What do we call these forces again? These forces are sometimes called bonds. As we have spoken during our first lesson, we talked about covalent bonds. These bonds are called interatomic forces because they are forces of attraction that exist between these atoms within a molecule. Okay, so when we talk of interatomic forces, they are bonding forces. They exist between two atoms. Found where? They are found between atoms within a molecule. Between atoms within a molecule. So one molecule of water, if we can get our hands on it, you would see, if it was possible to see with our naked eye, would see one molecule of water looking like this, and then you see that there's a force of attraction. If you imagine maybe two magnets, there's a force of attraction that is happening between the oxygen and the hydrogen. Okay, that force, the name of that force is given interatomic force. Okay, you can call it interatomic force, or you can just simply call it a chemical bond. So sometimes we refer to it as a chemical bond, sometimes we refer to it as an interatomic force. So it's just a new word. It shouldn't be something that is difficult to say. What are you talking about interatomic forces? We're simply talking about chemical bonds. They are found between atoms within each molecule. Okay, and it is important that we must say these things, they only affect the chemical property of the molecule. They affect the make of the molecule. Okay, so if I, for example, disturb this bond here, let's say I break it apart. Okay, I change the chemical make of this molecule. It's no longer water, because for us to talk water, we always have to have oxygen and two hydrogen. If now I have broken down, this hydrogen is no longer there. This can no longer be what? Water. Its chemical composition is no longer that of water. So it is very, very important that we talk of that. Okay, what about intermolecular forces then? Intermolecular forces, these are forces that are found between two molecules. Now, when we talk of molecules, water is going to have a lot of molecules. Okay, so water is going to have a lot of molecules. Then you are going to see these molecules, they are connecting, and then right, you see these molecules are connecting, and these molecules are connecting these, they are having forces of attraction there. So those forces of attractions are called what? Intermolecular forces. They are also attractive forces. Great talk. They are also attractive forces, and where do we find them? We find them between the molecules. We find them between the molecules. Okay, right. So we find them between the molecules, these ones, okay, and they affect the physical properties. These are the ones that are going to be affecting the boiling point, the melting point, the viscosity, and also affecting the what? Affecting the vapor pressure. Okay, but these ones are not going to be affecting the chemical make of the compound, because even if I separate the two, okay, if I come and overcome these attractive forces because I can overcome them. Maybe overcome them by maybe introducing heat, right, into the system. If I then overcome these forces, then I can separate the two molecules, okay? If I separate the two molecules, it is still the same chemical composition. I'm still talking about water, but now it's separated. Maybe it was the two molecules, the forces were strong together. It was in a form of a solid. So if I introduce heat, then they get separated. It is now in a form of a liquid. Introduce more heat, they get more separated. It is now in a form of a gas. However, we're still saying this is water in a form of a solid. This is water in a form of a gas. This is water in a form of a liquid. So when we are talking intermolecular forces, they only affect the physical properties. The way, if I can put it in general terms, the way the water looks, the way the water is. Is it solid ice? Is it water liquid? Is it water in a form of a gas? However, but the interatomic, if you were to separate, overcome those forces, you are going to change this chemical or compound completely from being water to being something else. Okay, so what are we going to be dealing with? We are going to be looking at overcoming the intermolecular forces. That's what we're going to be looking. We're not going to look at overcoming the interatomic forces. We just wanted to understand them. What are they and how do they work? So we'll be looking at overcoming the intermolecular forces, these attractive forces, overcoming them, right? Or even separating these intermolecular forces, the forces that are between two molecules. Okay, all right. And then how is that going to affect the physical properties of each molecule? Okay, so we're not going to dive too deep into understanding these intermolecular forces as to where they come from, what they are, grade 12. This will need a whole topic which will take days for us to go and understand these intermolecular forces, okay? What we need to understand is that for us, the intermolecular forces are going to be applied in organic chemistry. Simply put, intermolecular forces for us are just going to be applied in our 9 homologous series because that's where our organic chemistry is going to be centered around, our 9 homologous series, okay? So what I want you to know is that I want you to know like this. Well, the homologous, the intermolecular forces are called we have van der Waals forces, okay? And then under van der Waals forces, you will have those London forces, dipole forces, hydrogen bonding. But what I want you to know, or how I want you to know this, we're going to try and take a shortcut and say, we are just going to say we have 3 types of intermolecular forces. Those would be the London forces, sometimes called dispersion forces. Those would be the dipole forces, and those would be the hydrogen bonds. Now, a question would be saying, sir, if you are saying you don't want me to know, or you don't want me to stress about knowing what are these forces, how then can I identify to say this compound has these types of intermolecular forces, this compound has these types of intermolecular forces? Easy. Okay, since we said these intermolecular forces are going to only be applied in our 9 or on our 9 homologous series, then we are going to separate the homologous series according to the intermolecular forces that are found in each. Okay, I will repeat myself. We will separate the homologous series according to intermolecular forces that are found in each homologous series. For example, when we talk London forces, okay, they're called London forces or dispersion forces. I usually refer to them as London forces. So I'm going to be, for the remainder of this lesson, right, I'm going to be referring to them as London forces. But if you refer to them as dispersion forces, it is okay, right? So London forces, under London forces, or the homologous series that will have London forces in them are as follows. It's the alkenes, and the alkynes. Basically, we can say the what? The hydrocarbons. If you remember hydrocarbons from the previous weeks, okay? These are the compounds that contains only hydrogen and carbon atoms, or contains hydrogen and carbon atoms only. They are hydrocarbons. So the hydrocarbons all will have London forces between them. So the forces that will be holding the molecules of all these hydrocarbons are called what? London forces. Okay, right. Then we are going to say dipole-dipole forces. Where are we going to be finding the dipole-dipole forces? We will find the dipole-dipole forces in compounds such as aldehydes, ketones, esters, haloalkane. Now, it is worth noting, grade 12, that these ones, they also have London forces. Okay, so why is it that I did not put London forces here? To avoid confusion, I'm not going to put London forces here. I just want you to know it, keep it somewhere at the back of your head, that London forces are also there in an aldehyde. However, right, the intermolecular forces that are stronger in an aldehyde, the intermolecular forces that are stronger in an aldehyde would be the dipole-dipole. The intermolecular forces that would affect the physical properties of an aldehyde more will be the dipole-dipole forces. So, but London forces are there. So here you have London forces, here you have London forces and dipole-dipole. So if someone asks you for intermolecular forces in an aldehyde, I wouldn't expect you to start by saying London forces. What I would expect from you is to say dipole-dipole. And then if they ask for more than that, then you can say dipole-dipole and London forces. Okay, grade 12? Because they are there, but they are not the most strongest. The ones that are there, that are out there, that will make a ketone, that will make a ketone behave in a certain way, are the what? The dipole-dipole forces. Okay, and then again, we go to hydrogen bonds. We said hydrogen bonds are just a special type of what? Of dipole-dipole. So if they are a special type of dipole-dipole, that also means hydrogen bonds will also find what? London forces in them, but they are not the most important ones. Okay, the hydrogen bonds are found in alcohols and also in carboxylic acid. So it's very, very important that you are able to just simply separate the homologous series according to what? To the intermolecular forces that they belong to. Simply put, London forces, hydrocarbons. Okay? Hydrogen bonds. I usually start with the London forces and I do the hydrogen bonds. And I say to myself, whatever I have not counted must be going to the dipole-dipole. That's how I usually remember it. I said, okay, London forces, what will I find? I'll find alkanes, alkenes, and alkynes. Okay, hydrogen bonds, what will I find? I'll find alcohol and carboxylic acid. Whatever I have not counted out of the 9 homologous series must be going to dipole-dipole. That makes my life very, very easy in terms of saying I don't have to even memorize this. As long as I know my I5 cache table from previously, then it will be easy for me to memorize. I won't have to stress about it. Okay, so we said we must know these intermolecular forces, but we must also know them in terms of their strength. So as we talk of the strength here, the strength increases as we go in this direction. So what are we saying? When it comes to intermolecular forces, we will have the weakest here, very weak. The London forces are the weakest intermolecular forces that you can find in organic chemistry. Okay, and then followed by the dipole-dipole forces. These ones are strong. Dipole-dipole forces are just moderately strong. And then you will have the hydrogen bonds. These ones are the strongest. The strongest are the hydrogen bonds. They are very, very difficult to what? To separate. Remember, we said, what are we doing? We are looking at separating, we are looking at overcoming these intermolecular forces. So the hydrogen bonds are very, very difficult to overcome. They are very, very difficult. So if maybe we're introducing heat to try and overcome the hydrogen bonds or separate them, it will take very, very high temperatures or high heat for you to be able to do what? To overcome them and separate those intermolecular forces. It will take high also for dipole-dipole, but it does not take that much high for London forces. So that if you are given a molecule, right, and the molecule you're checking, it belongs to alkanes, then you can say, okay, this molecule is going to have relatively low boiling point if you're comparing this molecule to what? To a molecule such as ketone, for example. You will see it has a low boiling point. Okay, here's something also that I want you to know, grade 12, that I'm also not going to go to deep details on it again, right? for reasons of scope, our scope as a grade 12 learner doing technical science, I just want you to keep it somewhere in your head that all these compounds here, we say these are non-polar. These are non-polar molecules. We call them non-polar molecules. Okay, it's just keep it there. Just know it as something, even though you don't know why we call it as non-polar, because that will mean we have to go to deep things such as electronegativity that we really do not want to touch here. We will just want to say these are non-polar molecules. Okay, and then we are going to say these ones are what? Are polar molecules. These are polar molecules. And these ones, since these are just a special type of these ones are also what? Polar molecules. So let's just know that these are polar molecules, these are polar molecules, these are non-polar molecules. Okay, right. Okay, so what do we do with these intermolecular forces then? Okay, now we need to know a relationship between the intermolecular forces and the physical properties. What physical properties? It's the BP, it's the MP, it's the visco, and then it's the VP. Remember that? BP, MP, visco, VP. Always try and abbreviate it like that. Boiling point, melting point, viscosity, and vapor pressure. Okay, so if we have stronger intermolecular forces in a certain compound, that means that compound will take time for us to boil, if you are thinking about it, grade 12. So it means that compound will have a what? A higher boiling point. Okay? And if a compound has a higher boiling point, right, that compound will definitely also be having a higher melting point. So it means if that compound was in a solid form, it would be difficult to turn it into what? Into a liquid form, because of how it is, or how it behaves even when you are burning it. Okay, think about it. If you were to have an ice of honey, if you were to have honey turning into ice, okay, now you want to take honey from being ice to being liquid. It's not going to be as simple as when you turn water from being ice to being liquid. Do you understand? So the melting point of honey is also there high. Okay, what about the viscosity? If honey has a higher boiling point, honey has a higher melting point. But we also know that honey has a what? A very, very high viscosity as well. So this is how I do it with those arrows. Higher boiling point, it means that same thing will have higher melting point. It will have higher viscosity. But remember, what did we say? If something is difficult to boil, then something does not have a lot of vapor, then it means that thing will have a what? A low vapor pressure. So that's the relationship that we must know. We must know that stronger intermolecular forces means high boiling point, high melting point, high viscosity, and low vapor pressure. Okay, we must know that weak intermolecular forces will then means low of these things. So if the intermolecular forces are weak, then it means we are going to have low boiling point, we are going to have low melting point, and we are going to have low viscosity of that substance, but we will have high vapor pressure of that substance, because that substance will easily create vapor when we put it under heat. If I'm putting that right, you put that under heat, or you introduce heat into that substance, since it has low boiling point and low melting point, it will just quickly boil, right, and then it will turn into vapor quickly. Therefore, it will exert that pressure. Okay, so then it will have high vapor pressure. So that's how we are going to link these things. Once you know the intermolecular forces, now you link them to the physical properties, and then you create that relationship. So it means if I were to compare an alkene and a ketone, I can now maybe make an informed decision as to who do I think will have a higher boiling point between a ketone versus an alkene. Why? I know the intermolecular forces of a ketone are stronger than the intermolecular forces of what? Of an alkene. Therefore, I would say since the intermolecular forces are stronger, then it means it will have a what? A higher boiling point. A ketone compared to an alkene will have a higher boiling point. A ketone compared to an alkene will have a higher melting point. A ketone compared to an alkene will have a higher viscosity. But a ketone compared to an alkene will always have a what? A lower vapor pressure. So I can do that. Okay. So if I look at this, I can see that here I will have the highest boiling points around here the alcohol and the carboxylic acid. Why? Because they contain the strongest intermolecular forces, which are hydrogen bonds. So if I look for the highest of boiling points, I should find them here. These are things that will have the highest boiling point, they will have the highest melting point, they will have the highest viscosity, and they will have the lowest vapor pressure around these things. Okay, so, but what else can we say about alcohol and carboxylic acid? Well, their strength both between the two of them is not the same. If maybe I were to compare an alcohol and a carboxylic acid, I will find that the carboxylic acid will have even higher boiling point, because the hydrogen bonds within the two of them are not exactly the same, meaning that the hydrogen bonds of carboxylic acid will be stronger than the hydrogen bonds of the alcohol. And the reasons there is based on what we call the sites of bonding, as I will talk about it in a moment. What do you mean the sites of bonding? As I look at the factors, I will then look at that sites of bonding. Okay, right. Let's look at the factors that will determine the intermolecular forces. So, given a compound, right, you want to now determine which homologous series, which intermolecular forces, will I find in this compound. What are you going to look at? You should look at the following factors, Creator. These factors are going to help you. First, check the time, as I was doing comparison between an alkane and a ketone. Let's check the type of the organic compound. To which homologous series does this compound belong? If the compound belongs to carboxylic acid, this compound will have the strongest intermolecular forces, right? Just simply from the diagram that we had previously. If the compound belongs on alcohol, it's going to have very strong intermolecular forces. If we compare it to what? If we compare it to a compound that is here. So the first thing you want to do, check the type of the organic compound. Compare the type of organic compound, and you see, then you can take a decision, an informed decision, as to which intermolecular forces are you going to be finding there. Okay. Number two, check the molecular size or molecular mass. Okay. How big is this compound? The molecular size and molecular mass. Think about it. Okay. As much as it is simple to boil water, okay, but if you have water in let's say 1 liter, okay, 1 liter pot, and water in a 5 liter pot, right, and these two are exposed under the same heat, the heat that is they are exposed under is the same, who's going to boil faster? The 1 liter. The molecular size matters. Okay, the molecular size matters. So it will tell you that the intermolecular forces here are going to be stronger on the one with the larger size compared to the one with the smaller size. So the size of the molecule matters. Okay, you might be comparing the same things now, because here we're comparing things that were not the same. On factor number one, we're comparing the one thing that belongs to alkanes, another thing that belongs to what? To ketones or alcohol. You're saying, well, I know for a fact that alcohol is going to have the strongest intermolecular forces. Okay, therefore, this is not even up for debate. This one is going to be difficult to boil or even melt. But now you are comparing the same now. Let's say you are comparing both under alkanes. Both of them are alkanes. So what can I look at? I can look at their size. How many carbons does this one have? Right? Like here, this one is 1 liter, this one is 5 liter. That's an example I'll make for you. Simply, if you think about it, exposed under the same heat, the 1 liter one is going to boil easy or faster, and then the 5 liter container will take time to boil. Okay, so that tells you that the intermolecular forces here, if you compare between them, will be stronger on the 5 liter. It will take time for you to separate them. It will take time for you to overcome them and change this from being a liquid to a gas if you are boiling it, for example. Factor number 3 that I want you to look at is the branching. Okay, because most of the time we'll also be given, well, names also and structures. If you're given a name, please turn it into a structure. Always try to work with structures. Okay, check the branching there. Okay, check the branching. If a compound is more branched, this compound will be easier to overcome its intermolecular forces. A compound that has more branches, for example, if I have 1, 2, 3, 4, a compound that looks like this, okay, this would be a butane, this would be a butane, a compound such as butane, okay, and then a compound like this one, I'll call this maybe compound A, a compound like this one, okay, they all have the same number of carbons. I hope you can see that. They all have the same number of carbons, okay? So meaning that it's that we're in this case, we are comparing the same things because they all have the same number of carbons. However, the difference is that this one is more branched, okay? So if you branch it, it's like you are allowing for it to feel the same heat more, if I can put it like that in inverted commas there, grade 12. It's like you are allowing it to get more of the heat than this one because this one is spread out. It's all over the place. It's huge. Okay, so this one, because it is less branched, it will have its intermolecular forces will be difficult to overcome compared to this one. Its intermolecular forces here will be easier because of its branching, because of how it has been branched. It has been put maybe in a container that is small, making it to feel more fire. I'm just making an example, making it to have to feel more fire than the other one, which was in a bigger container. This is trying to give a general example there of why with the more branched one have lesser intermolecular forces or weaker intermolecular forces would be the correct way there. So if it is more branched, it will have weaker intermolecular forces compared to the one that is less branched, less branched. So we are also going to check the branching. So these are the things that we are checking. And remember, grade 12, this is really simple to do. This is not difficult to do. Just I check type of bonding, type of organic compound, I mean. If the type of organic compound is the same, okay, next thing, is the molecular size the same? If the molecular size is the same, right, in this card, the type of compound is the same. Both of them are alkanes. Next, molecular size. What about the molecular size? Well, both of them have 4 carbons. That means that both of them will also have the same number of what? Of hydrogens, okay? Same number of hydrogens. So that means molecular size is the same. What's my next thing to check? Branching. Are they branched the same? No. This one is more branched. I found my answer. The one that is more branched will have weaker intermolecular forces. The one that is less branched will have stronger intermolecular forces. Okay? The last one is what we call size of hydrogen bonds. Size of hydrogen bonds. What is this hydrogen bond we are talking about? This is a bond between a hydrogen and oxygen in our case. Could be a bond between hydrogen, oxygen, a bond between hydrogen, nitrogen, bond between hydrogen and fluorine. However, for us, it will be a bond between hydrogen and oxygen. And where are we going to find that bond? We are going to find that bond between or alcohols, or we'll find a bond in a carboxylic acid. Okay, right. So for an alcohol will look something like this. Most simple alcohol will look something like this. Okay, this is one molecule of alcohol. Let's put another molecule of alcohol here. Okay, it will look something like this. Now, these two molecules will have forces of attraction between each other, where the oxygen will be attracted to the hydrogen. I hope you can see that force of attraction that I'm trying to show there. That would be the force. Here is the force between hydrogen and oxygen. And since we already have this force, we cannot now have it here as well. Okay, this would be wrong. It can either be in this one or in this one. Okay, so this we call a site. It is a site of a hydrogen bond. It is called a site of a hydrogen bond. Okay, let's make the same example but for carboxylic acid.
Carboxylic acid will have a double bond O with O and a hydrogen. Okay, this will be carboxylic acid. Let's check another one. Carboxylic acid, double bond O with O and H. Okay, so here, since there is this double bond O, this double bond O can have a side with this hydrogen. Okay, this double bond O can have a side with this hydrogen. Okay, once this double bond O has a side with this hydrogen, this one on the other side could also have this one could also have a side here. So this oxygen could be bonded to this hydrogen here. So we have a hydrogen and the oxygen bond, hydrogen and the oxygen bond. So when you check these sides, it's one side, it's two sides. You have two sides of hydrogen bond when we're talking carboxylic acid. So we say carboxylic acid have two sides of hydrogen bonds. We say alcohol have only one side of hydrogen bond. So this difference in side is the one that affects and makes alcohols to be weak or weaker when compared to carboxylic acid, because they are not really weak, but they are just weaker when compared to carboxylic acid. So these ones, they become the strongest. They become the strongest. So none is stronger than the hydrogen bond, at least in our scope of grade 12 technical science. None is stronger than the carboxylic acid. So if you can do this, then you can answer the questions, grade 12. Then you can answer the question, especially the most famous question that we always cry about when we're talking about these physical properties. I call it the 3 or 4 marks question. Okay, let's talk about the 3 or 4 marks question before we can answer it together. I'll answer this one for you, but the next one I'll give it to you and you will try, and I want to see if you can answer it. Okay, so but I'll give you a sort of a plan as to how you should answer this. I call it a 3 or 4 marks question. That's what I call it. It's very easy to answer. Number one, I always say, if you want to answer here, it will always be comparison. They will always be asking you comparison or a trend, okay? But there will always be a difference here. You must always remember your factors. What are my factors? Type of the molecule or type of the organic compound. It's type of the organic compound. Those are the factors. And then you look at the branching or molecular size, type of organic compound. You look at the molecular size, you look at the branching, or you look at the size. So these are the things that you are going to look. And you are going to look at these things, and then you are going to compare them to the physical properties. How, before the physical properties, you identify the intermolecular forces that are going to be going with these ones. Okay, then from there, you look at the physical properties. Okay, how do you do that? For example, here they're saying which of the following compound will have a higher boiling point. Okay, to answer this question, I'm not going to write a paragraph. Okay, grade 12. I don't want you to write a long paragraph where you are going to be trying to convince me. It is unnecessary. Just try to be precise, go straight to the point, and maybe even write it in point form. Don't even connect your sentences. It's not necessary to even connect those points. Just go straight to the point and say, I'm dealing with this question. What am I going to look? I want you to check first the difference in the structure. Okay? If given a structure. If not given a structure, have to draw a structure. Then you'll be able to do that. So check the difference in the structure. What's the difference in the structure here? I look at A. I see A has a double bond between the carbon atoms. I see B here has a formyl group. That's the difference in the structure. Both of them have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. So their molecular mass should be relatively the same. Okay. Then what the main difference here is their functional group. This one belongs on alkenes. If I look at the double bond, this one belongs on aldehyde. So by that, I've already identified the intermolecular forces. To say alkenes, I know they have London forces. All right. Aldehydes, they have dipole-dipole. Okay, I've already identified it. So I've looked at the difference in structure. Okay, so once I've looked at the difference in structure, the second thing I'm going to talk of here is the strength and type of intermolecular forces. The strength and the type of intermolecular forces. To say which one is going to be will have stronger intermolecular forces, because that's the one that should have a high boiling point. Which one will have the stronger intermolecular forces, and what are those intermolecular forces that I'm talking about? So I must mention the strength, and then I must mention the type of the intermolecular forces. And then lastly, I will talk about, well, not lastly, but I will then talk about the energy needed to overcome. I usually say overcome, some people say separate. So you can say overcome or to separate the intermolecular forces. The energy needed to overcome the intermolecular forces. You follow this, I'm telling you, great job. It will make it easier for you. It is sort of a structure that always guides me into answering this question. And then lastly, just conclude. So you're making a conclusion based on the question that you were being asked. If you do it like this, it will be precise, it will be straight to the point. Even the person who's marking you is not going to be frustrated to say, what is this person saying? So let's look at A and B. What are we saying is the difference in structure there? Which of the compound will have a higher boiling point? Well, first we must choose which one will have a higher boiling point. Just by simply looking at that, I'm going to choose compound B, because I already know that the dipole forces, intermolecular forces, are stronger than the London forces. A has London forces, B has dipole. So B must have a higher boiling point, because the stronger the intermolecular forces, the higher the boiling point. The stronger the intermolecular forces, the higher the melting point. The stronger the intermolecular forces, the higher the viscosity, and the stronger the intermolecular forces, the lower the vapor pressure. Do you remember that? BP, MP, visco, VP. Higher this, lower this. Always keep it somewhere at the back of your brain then. So I'll just simply choose, I would say compound B has a higher boiling point. Now I need to go further in explaining. When I explain, I have to talk about what is the difference that I'm seeing when I'm looking at their structure. I would say myself, compound B contains a formal group, right? By saying that, it tells me that compound B belongs to those dipole. Compound B contains a formal group. Okay, right? And then I continue because I'm answering in terms of compound B, right? Compound B contains a formal group. Compound B has stronger intermolecular forces, right? Then I usually open a bracket to identify those intermolecular forces. Has stronger intermolecular forces, dipole forces, I close the bracket. Then compound A, remember I'm comparing, so I must show that comparison. Has stronger intermolecular forces, then compound A, which has London forces. I would usually put that in bracket. Then I say more energy is needed to overcome the intermolecular forces of compound B than those of compound A. Again, there I'm doing what? Comparison. Then I say the higher the intermolecular force, or the stronger the intermolecular forces, the higher the boiling point. That's why I chose compound B. That's why part I did not write it. I'm just now telling you, okay? That's why I chose compound B. Formally, I would write it like this, something like this. Compound B contains a formal group. By saying this I identifying the difference in their structures. If I was talking about A, I would say if I answered based on A, because you could also do that, I would have said compound A contains a double bond between carbon atoms. That's the difference between the two. The other one does not. And then, but I'm doing according to compound B. Let's do compound B and then finish. Then I'll say compound B has stronger intermolecular forces. That's me talking about the strength of the intermolecular forces. And then in bracket, I just simply to show that I know the strength and I also know the type. In bracket, I simply say dipole, close the bracket. Then compound A. Why? I am comparing between the two compounds. Okay? And then A has London forces. Okay, that again tells the marker or the person who's marking that this person knows these things that they are talking about. Then I say more energy is needed to overcome, or someone would say separate. More energy is needed to overcome the intermolecular forces of compound B. Okay, than that of compound A. Unnecessary, I didn't put it there. Then I then conclude that the stronger the intermolecular forces, the higher the boiling point. So this is the reason why I chose compound B. If I just simply write it like this, and if you can check, it's in point form. There is no way where I'm saying because, then, hence, therefore. There's no way where I'm putting all those words which are just connecting, where I'm just trying to play with the English. I'm not sure of my English. Let me just go straight to the point and use science. Okay, I am aware of all these words because I always use them as I am learning. So I just go straight to them. Okay, so here's what I'm going to do, grade 12. I'm now going to give the next one to you, and I'll give you 3 minutes to do it on your own, and I want to see if you can do it. Remember, you check the difference in structures, okay, and then you check the strength and the type of the intermolecular forces, the energy that is needed, and then you conclude. And remember, you are checking those factors. The factor that we're checking here, it was different types of organic compounds. Okay, they belonged in, one was belonging on alkene, the other one was belonging on aldehyde. It was an aldehyde, so they had different intermolecular forces. So let's check if you can try this one and do it on your own. All right. Right, great job. Welcome back. I hope you've tried the question and I hope you got it correct. Okay, let's look at the question now and say, it says, which of the following compounds will have a higher melting point? And we are also asked to explain. So we're still dealing with the 3 or 4 marks question. This is what I want us to deal most, because if someone can answer this 3 or 4 marks question, or a learner can answer this 3 or 4 marks question, any other question that could be asked in question 3, physical properties, should become simple for them to answer. And this, again, if you just follow that structure, it is simple. So here they've asked it in terms of melting point. So let's again stop this mentality of thinking it must also be asked in terms of boiling point every time. And then once they ask it in terms of melting point, we don't know what to do. We remember there's a relationship we have created. We have a relationship between BP, MP, V score, and VP. So if you know something about the boiling point, that means you know something about the melting point. That also means you know something about the viscosity. That also means you know something about the vapor pressure. If I know that the boiling point of this compound would be high, then that means I know that the melting point will also be high of this compound. That means I know that the viscosity will also be high. That means I know that the vapor pressure will be low. So as long as you know something about one of these physical properties, you know something about all of them. So just because it was not asked in terms of the boiling point, doesn't mean now it must be wheels coming off, then the car is turning upside down. No. It's asked in terms of which one has a higher melting point. I can think of it in terms of boiling point, then I can answer by writing melting point. So if I look at my factors, which factor here is the one that is going to be determining by intermolecular forces? Let's check. Are they having the same homologous series? Are they within the same homologous series? And the answer is yes. So it's no longer the first one where we were saying it's type of the organic compound, in which homologous series does it belong. These ones, they belong on both. So I can't say. So it means they have the same type of intermolecular forces. They all have dipole-dipole. They are ketones. If you know your R5 catch table there, these ones are ketones. These are ketones. So if both of them are ketones, they must be having the same intermolecular forces. So how am I going to answer this one? I go down the molecular size. Oh, I check. This one has 3 carbons, 1, 2, 3. This one has 1, 2, 3, 4, 5, 6 carbons. The sizes of these things are not the same. So which one is going to have a higher melting point? Definitely the one that is going to have a higher melting point is compound B. Compound B is going to have a higher melting point. Definitely. Okay, so then I have the market list for choosing. Okay, now it's time to do what? To explain. How am I going to explain? Look at the structure. What's different about the structures? Okay, 2, strength of the intermolecular forces and the type, and then 3, energy needed to overcome the intermolecular forces. Then I conclude. Okay, so what am I going to say? Compound B, I've chosen. Then I should say something along the lines as if I was to answer according to compound B. I'll say compound B. Compound B, the longer chain than compound A. That's the difference in their structure. Okay, that's the reason why this one will have stronger intermolecular forces. Compound B has a longer chain than compound A. Compound B has a longer parent chain, if you like write it in full, than compound A. That's the first thing I'm going to say about it. And it's true. Compound B has a longer carbon chain than compound A. Then on the next point, if it has a long carbon chain, then compound B has stronger intermolecular forces. Then I simply open the bracket to indicate the type of the intermolecular forces. I will say dipole forces, right? Then compound A. It's also dipole forces, so I don't need to indicate that one. So I'll say compound B has stronger, I'm indicating the strength of the intermolecular forces. Compound B has stronger intermolecular forces than compound A. Then I'll say more energy is needed to overcome the intermolecular forces of compound B than those of compound A. Then I would say the stronger the intermolecular forces, the higher the melting point. I should be getting everything that is asked there. You can answer this question in terms of saying it as compound B. Usually I go for that one, but it could also be answered in terms of compound A. Okay, Remember, you have chosen compound B as the one with the higher melting point, but your reasoning can be based on compound A. Why are you saying compound A? You could say compound A has a shorter parent chain, than compound B. Remember, you are comparing. So the issue of comparison should always be there. That's point number one. And what do I say? This is point number two. I'm answering in terms of compound A. Compound A has weaker, they are weaker intermolecular forces. In bracket, I say those intermolecular forces are what? Dipole. Compound A has weaker intermolecular forces, dipole, than compound B. Remember, I am comparing. Then I will continue and say, I'll continue here. Then compound B, then I would say less in this case, not more, because it has weaker intermolecular forces. So it means less energy is needed to overcome the intermolecular forces of compound A. And then to conclude, I would say the higher or the stronger the intermolecular forces, the higher the melting point. Just simply put it like this in terms of these points, and then you are able to, you have answered your question correctly. So quickly go through there. I've chosen in terms of compound B. Compound B has a longer chain than compound A. That's the difference in the structure. Compound B has a stronger intermolecular forces, dipole, than compound A. More energy is needed to overcome the intermolecular forces of compound B than those of compound A. The stronger the intermolecular forces, the higher the melting point. I've answered that question again. So that was factor number 2, where we were having the same homologous series, but we were having different molecular sizes. Okay, let's look at number 3. Okay, which of the following compounds will be more viscous? You see now, they are asking in terms of what? Viscosity. You shouldn't panic. Now it's being asked in terms of viscosity. I don't know what to do. As long as you know something about one of them, you know something about all of them. Remember, BP and MP and visco and VP. Higher means higher, means higher, means lower. Lower means lower, means lower, means higher. Just know this thing, and it's going to make your life very, very simple. Which of the following compounds will be more viscous? The one that is more viscous should be the one with the higher boiling point. Which one will have the higher boiling point? It's this one. This one will be more viscous again. So simply choose compound A. Okay? Explain your answer again. What is the different structure? Compound A is less branched than compound B. Okay? Not difficult, this thing grade 12. Compound A is less branched because here we are talking branching. They have the same homologous series. They have the same molecular size. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the molecular size is the same. The only difference is the degree of branching. So compound A is less branched than compound B. Compound A has stronger intermolecular forces, London forces, than compound B, which also has London forces. Okay, more energy is needed to overcome the intermolecular forces of compound A. All right, the higher or the stronger the intermolecular forces, the higher the viscosity. I could answer it in terms of compound B. Compound A will be the one that is more viscous. Okay, compound B is more branched than compound A. Okay, compound B has weaker intermolecular forces, open bracket, London forces, close bracket, than compound A. Okay, less energy is needed to overcome the intermolecular forces of compound B. than those of compound A. The stronger the intermolecular forces, the higher the viscosity. As I have been saying, compound A here, compound A is less branched than compound B. It's true. We've seen that compound A has stronger intermolecular forces. If it's less branched, it means its intermolecular forces are what? Are stronger. And those intermolecular forces are London forces than compound B. That means more energy is needed to overcome the intermolecular forces of compound A. Okay? And the stronger the intermolecular forces, the higher the viscosity. So I'm showing you, you can answer this question whether it's asked in terms of boiling point, whether it's asked in terms of melting point, is asked in terms of viscosity, even if it's asked in terms of what? Vapor pressure. You should be able to answer this question very, very easy. You follow simple steps. And what are the simple steps that we are talking about? Look at what is the difference in their structure. This is going to inform you even the factor that is being assessed here, because there are these factors that could be assessed, the four of them. You could assess the type of the organic compound, meaning the homologous series to which they belong. Okay, they could assess the molecular size or molecular mass. All right, what is the masses of these two? The difference in their masses could have a difference in their intermolecular forces. Okay, and then the branching, meaning in that case they are in the same type, they have the same mass, but the branching is not the same. So in that case, again, the one that is less branched will have stronger intermolecular forces than the one that is more branched. Okay, repeat, the one that is less branched will have stronger intermolecular forces than the one that is more branched. Just think of it. If we talked about organic chemistry when we started as a chemistry where we have long chains, carbon is able to form long chains. Now, if you're having those long chains, imagine something that has millions and millions of chains, comparing it to something that only has 2 chains. Just because they belong in the same homologous series does not mean they are now going to have the same then does not mean they are now going to have the same boiling point. They can't. Okay, this one has a greater mass. Okay, or this one has a straight chain of all these millions, while these other ones, they are put such that they can fit in this place. The other one is a straight, very long chain. This one they are put such that they can fit here. They are made in branches. It means this one will be able to experience the heat if maybe they are being put under heat than the one with the longer chain. So making it to have less intermolecular forces there. I hope you get me then. And the last one would be the size of what? Of hydrogen bonding, which is the one that we are going to look at now. Okay, the next one here, they are saying which of the following compounds will have less vapor pressure. Again, this one is asked in terms of vapor pressure. Again, if you can check these questions we've dealt with, one was asked in terms of boiling point, one was asked in terms of melting point, one was asked in terms of viscosity, one was asked in terms of what? Of vapor pressure. Again, I've said, once you know one thing about one of them, you know something about all of them. If I know by looking at them that this one will have a higher boiling point, I repeat, then it means that same one will have a higher melting point. The same one will have a higher viscosity, but that one will have a what? Lower vapor pressure. If I know that this one will have a lower boiling point, then it means it will also have a lower melting point. It means it will also have a lower viscosity, but it will have what? Higher vapor pressure. Okay, so here they were being asked, and here we are comparing a carboxylic acid. If you can see here on compound A, this is a carboxylic acid, and in compound B here is a what? An alcohol. So these are being compared, and we must say which one is going to have less vapor pressure. The one that has less vapor pressure must be the one that has the highest boiling point. Okay, the one that has less vapor pressure must be the one that has what? Highest boiling point, because higher boiling point, higher melting point, higher viscosity, less or lower vapor pressure. So the one with the higher boiling point must have the less vapor pressure. So which one is that? It must be this guy here, compound A. It must be compound A having a less vapor pressure there. Why will compound A have a less vapor pressure? Let's look at our factors. Are we looking at a factor where they are different in terms of the homologous series? Yes, in this case, they are different in terms of the homologous series. One is a carboxylic acid, one is an alcohol. But what we know about these two is that both of them are the strongest. So we're having the strongest here under the hydrogen bond. As much as they have different homologous series, they have the same intermolecular forces, which is hydrogen bond. Both of them have hydrogen bonding. Both of them have hydrogen bonding, which is again our strongest. It's our strongest intermolecular force at our level. Okay, so both of them have hydrogen bonding. So we know that both of them have hydrogen bonding. So how are we going to differentiate between the two? Remember, they do not have the same site. As you can see here, these hydrogen here and these oxygen here, they can be what? Having a site with the other molecule. So you have a site coming in here, you'll have another site here. But here in this case, we'll only have one site. So the sites, they will definitely have a major impact or a major effect on the boiling point, melting point, viscosity, and vapor pressure of these compounds. So this one would say this is the compound that has a what? The less vapor pressure. Even though you can see it only has one carbon, this one has 3 carbons, but this one is going to have what? Is going to have a higher boiling point, making it to have higher melting point, higher viscosity, and a lower vapor pressure. So how will we answer this question here? We would say compound A has the less vapor pressure or the lower vapor pressure. Why? Compound A contains 2 sites of hydrogen bond. We're comparing compound A contains 2 sites of hydrogen bonds. As we have looked at it, contains 2 sites of hydrogen bond. Compound A, and then compound B contains 1 site of hydrogen bond. We've talked the difference between them, or the difference in their structure. Compound A has stronger intermolecular forces, which are hydrogen bonds, or hydrogen is supposed to say hydrogen bonding here. Hydrogen bonding. Then compound B, right? Then more energy is needed to overcome the intermolecular forces of compound A and that of compound B, even though it's unnecessary to put it there. The stronger the intermolecular forces, the lower the vapor pressure. This is the relationship here. Stronger the intermolecular forces, the lower the vapor pressure of any given compound. So if you are able to just answer all these questions that we have dealt with grade 12, and I've done a lot of them, and I hope by the time I was getting to this one, which was my last one here, I hope by that time you are getting the idea as to how to go about answering this question. Because if you can answer this question, that means you can identify the intermolecular forces in any molecule. That means you can identify which one will have a less vapor pressure. You can easily identify all these physical properties. If you can answer this question, there is no question that you cannot answer when it comes to question 3 of physical properties, organic chemistry. Okay, so this will be your homework. I want you to simply look at that. The table below shows 2 organic compounds with their corresponding boiling points. In this case, you are given. Right? Identify the type of intermolecular forces of the compounds in the above. Then explain the difference. It's given 3 marks. They are telling you, talk about the chain length, talk about the strength of intermolecular forces, talk about the energy, as I've been trying to show you them. Define the term melting point. You should be able to do that. Which one of the 2 compounds in the table have a higher melting point? The one with the higher boiling point. We should know the relationship by that one. All right. Which one of the 2 compounds have a higher melting point? Explain the answer in question 3.4. You should explain that. How does the vapor pressure of a compound compare? Okay. So this will be your homework, and I hope you should get it right. Summary for the day. Are you able to differentiate between intermolecular forces and interatomic forces? As these ones that are between the 2 molecules, these ones chemical bonds, these ones giving you the chemical composition, these ones, and this one only talking about the physical properties. Are you able to differentiate? Do you know and are able to define all physical properties? BP, MP, Visco, VP, right? Do you know the different intermolecular forces according to their strength? London forces, double forces, hydrogen bond, London being the weakest, dipole strong, hydrogen the strongest. Know the factors determining the intermolecular forces of the compound. Are we talking the same organic compound here? within the same homologous series, or are we looking at molecular mass or molecular size? Are we looking at branching, or are we looking at sites of bonding? Can you use all the vectors to answer the questions based on the physical properties? Okay, so that will be our summary for the day. Preview for our next lesson. Our next lesson will take place on the 11th of April 2025, and the same time, which is 4 o'clock up until 1400 hours up until 15:30. We'll be looking at organic chemistry reactions there, grade 12. Okay, and with that, I thank you.